We want to start this program with a little bit of background on explosives and explosions. That is, what they are, what causes them, what the different kinds are, and that sort of thing. Essentially, an explosion is just a sudden or violent release of energy. It's usually accompanied by heat and gas. The important thing to remember about an explosion, unlike a fire, is that an explosion generates a shock wave. So unlike the fire in your fireplace, or unlike a structure fire, an explosion generates a shock wave. Explosives are generally classed into two categories: low explosives and high explosives. Low explosives propagate the explosion by burning. Explosives people call the kind of burning that low explosives do, they call that deflagration, which is just a really kind of a fancy term for burning. What that means is you get the initial little piece of the low explosive that explodes, and then as that releases heat, it burns the next little piece of explosive, and the explosion propagates by the burn front. Low explosives generally propagate, depending on the exact circumstances, but a good rule of thumb is at 3,300 feet per second or less. Low explosives are usually mixtures of a combustible substance, that is something that burns, and an oxidant, that is something that supplies oxygen. When we say it's a mixture, what we mean is you have two physically separate compounds that are just physically mixed together, and that forms a low explosive. Low explosives are generally used as propellants, like in rockets, or for pyrotechnics, like in fireworks. By contrast, high explosives propagate the explosion by the shock wave. That is, it is the propagation of the shock wave that detonates the next little piece of explosive, or the next part of the explosive that it comes in contact with. And high explosives, of course, propagate at generally greater than 3,300 feet per second. Another difference between low and high explosives is that high explosives are generally compounds. That is, it's not a physical mixture of two different chemicals. It is a single chemical. A single chemical compound generally forms a high explosive. The other important thing to remember is that an explosive that burns, that deflagrates in open air, may explode or may detonate if it's confined. To illustrate that last point, for instance, consider something like gunpowder. If you take gunpowder and just put it on the table and put a match to it, you'll see it just burns. However, you can find that in something like a pipe to make a pipe bomb, and it will explode. High explosives are further categorized into three different types. That is, primary, secondary, and tertiary explosives. Now, primary explosives are extremely sensitive to shock, friction, heat, or some kind of insult. As a general rule, they're compounds that are sufficiently sensitive that they can be set off with a blow from a hammer, and a good example is something like a blasting cap. Secondary explosives, sometimes called base explosives, are relatively, that is relative to primary explosives, relatively insensitive to shock, friction, heat, and other kinds of insults. And a good example of secondary explosives, a good example of common compounds that we come across are things like dynamite, TNT, RDX or C4, PETN, HMX, etc. Secondary explosives require a primary explosive to detonate them. That is why if you have something like C4, you need to have something like a blasting cap inserted into it to set off the C4. Tertiary explosives are even less sensitive to some kind of insult, like heat, friction, shock, or electrical stimulation. Tertiary explosives sometimes go by the term blasting agents, and tertiary explosives are insensitive enough to shock that they can't be detonated with a practical quantity of a primary explosive, something like a blasting cap. That is to say, the amount of blasting caps that you would have to carry around to set off a large amount of a tertiary explosive would just be impractical or too dangerous. So therefore, to set off a tertiary explosive, you need a secondary explosive, which of course needs a primary explosive to detonate it. So the way you would set off a large quantity of a tertiary explosive, a blasting agent, something like ANFO, which is ammonium nitrate and fuel oil mixed together, the kind of thing that blew up the Murrah building in Oklahoma City, is that you would have a blasting cap, a primary explosive, inserted into a quantity of a secondary explosive, which is then inserted into the large quantity of the tertiary explosive. So you would need 3 kinds of explosives to set off that chain and get that large explosion from that large amount of something like ANFO. And this is shown in slide 8. Now, any kind of explosive requires 2 elements. It requires a fuel, that is something to burn, and it requires an oxidizer, that is something to provide the oxygen. Any kind of fire requires this as well. Obviously, in your fireplace, the fuel is the wood and the oxygen is the oxygen in the air. Structure fires, the same thing. The problem, if you're trying to create a large amount of energy release, is that the oxygen in the air is a very diffuse and not concentrated source of oxygen. If you want to create a large energy release, you need to have a very concentrated source of oxygen right next to the fuel, and that's what explosives are. They're a mixture of fuel and oxidizer. So in an explosion, the oxygen comes from the chemical part of the explosive that supplies the oxygen, and that's the oxidizer part of the explosive, unlike a fire, which draws the oxygen from the air. Now, slide 10 gives you an example of some common fuels that are used in explosives. Some common hydrocarbons that we're all familiar with are things like fuel oil and turpentine, even sugar, wax, Vaseline, even sawdust or glycerin. So you can see that some very common compounds can be used to provide the fuel part of an explosive. There are even more energetic hydrocarbon-based compounds, things like nitromethane, which is racing fuel, nitrobenzene, ethyl nitrate, and there are some other common compounds that are usually called elemental fuels, things like powdered aluminum or magnesium, phosphine or hydrogen sulfide. The thing to remember about this slide is that the fuel part of an explosive can be found easily and bought readily because the fuel part of an explosive can be made or can be provided by so many common compounds. So putting together an explosive isn't really, pardon the pun, rocket science. If you can get a common fuel, combine it with a common oxidizer, and detonate it with something like a blasting cap, you're good to go. Now, in terms of the oxidizers themselves, we don't want to get too detailed. Just a little point to remember, perhaps, is that the oxidizer itself, the oxidizer part of the explosive itself, consists of 2 elements, or two components. That is the bonding agent and the oxygen supply. And these 2 combine to form the oxygen source. And you get something like, if you take ammonium as the bonding agent and nitrate as the oxygen supply, they combine to form ammonium nitrate, which is, of course, fertilizer, which is the oxygen supply. A rule of thumb with oxidizers is that many oxidizers that are used in criminal bombs and in ATE, ITE, or IDE. And the list is here, things like nitrate, peroxide, chlorate, chemical names like that. Chemical names that end in one of those 3-letter suffixes are often explosive oxidizers. And another common oxidizer that doesn't meet that rule but that is commonly used in criminal bombs is nitric acid. So following through with combining an oxidizer and a fuel, you get compounds like ammonium nitrate, which is the oxidizer, and fuel oil, which is the fuel, to form ANFO. Everybody knows what ANFO is these days, and it has a lot of uses in construction and even agriculture, so it's a very common thing. You get potassium chlorate and sugar to combine. The potassium chlorate is the oxidizer, sugar is the fuel, or nitric acid and urea to form urea nitrate. You also want to keep in mind that a lot of high explosives like TNT and RDX and PETN, C4, are actually chemical compounds. They're not mixtures. And in this case, you don't have the suffix to go by, that ATE, IDE, etc. suffix. So they're a little harder to pick up on, except that they tend to come packaged like what you normally think of as explosives. And you normally think of them as explosives or explosives packaging because you've got some exposure to it on TV and the movies, and in fact, they don't do too bad of a job of portraying what these things look like in their native form when they come from the manufacturer. So you're just going to have to rely on your sense of what these look like from what you've seen. They also might have commercial or military markings indicating that they're explosives or giving you a clue that they might be explosives. Keep in mind, though, that many high explosives like C4 can be molded into almost any shape and can, with some creativity on the part of the criminal, can wind up looking like almost anything. So you may not recognize it if it's been camouflaged in that way. You also want to be aware that there's another class of explosives which are peroxide-based, and you may have heard these terms, HMTD, TAPP, TATP, MEKP. If you hear them, they're just referring to a peroxide-based explosives. And peroxide-based explosives are usually very unstable and very dangerous. So if you come across these, or if you know you're coming across these, just exercise a lot of caution. Now, what exercise caution usually means is get the heck out of there if you can. If you don't have a job that you have to do. If you see anything that you suspect might be those compounds, you're in a very dangerous spot. Create a lot of distance between you and it, and between your teammates and it. And what's kind of insidious about some of these peroxide-based explosives are that HMTD and TATP look like crack or meth. And so a lot of cops have been injured when they use their drug test kits on these, because the drug test kits cause these things to have a violent explosion. So these peroxide-based explosives are very dangerous. They do look like crack or meth, but there isn't really any one or two clues we can give you to let you know that they're in your presence. You've just got to be aware of them, be aware of your surroundings, be aware of the context that you're in. I mean, if you know you're going into a drug house, you want to be a little extra careful about looking for things that might have an explosive content to them. And if you see those, if you don't have to be right there, right then, get out of there. And slide 15 gives you a little story, a little case study of what happened to a meth lab unit in Phoenix. Because these officers paid attention to their surroundings, and what they saw and what the suspect said, they wound up not getting hurt by some dangerous chemicals that were in there. They were, in fact, explosive. Didn't have to be a police unit. It could have been a fire agency responding to reports of a fire. It could have been EMS or whatever. The point is to pay attention to your surroundings, listen to what people are telling you, and don't try to be a hero. If you think that might possibly be some kind of high explosive, then back away and get the experts, which is the bomb squad there. Now in the next couple of slides, we show you some examples of various kinds of explosives. You can see when we said earlier that TV and the movies don't do too bad of a job, that these photographs of real explosives don't look too different from what you might have seen in the movies. But for instance, take a look at slide 17. You can see the slurry gel mixture over there. I mean, that could be anything, especially if it didn't have any markings on it. So something packaged like that, though, the purpose of this program is when you see something packaged like that, that your antennae should go up, and the little red lights should start going off in your head, and you should start to wonder if it might be an explosive. So the more clues to that will come from your surroundings, from the context, etc., from the people, from what they're saying there. On slide 18, you can see TATP looks like it's a white powdery substance. It would be hard to know that that's not crack or some other white powder. You can see that explosive even comes in sheets. If you look at slide 19, this is a sheet explosive that's either PETN or RDX. It's called data sheet, which is the commercial name for it, and it's just like a thick piece of paper, and it can be molded or just laid flat anywhere, and it's very explosive. On slide 20, you can see some C4, and if you didn't know it already, it's obvious that this can be stretched and molded and really made to be almost any shape. Part of what this program is about is to help you recognize bombs or bomb-making material when you come across it, when you're there for some other legitimate reason, doing part of your job. And so recognize that bombs consist of 4 components. There's the explosive or the explosive chain. There's the initiator, typically something like a blasting cap or a fuse. There's a power source, because something has to provide the power to the initiator, and that's usually a heat source like a match, or more commonly probably something like a battery, a timer. And then you have the switch, which is what connects the power source to the initiator. So those are the 4 components that make up most of the criminal bombs that are used these days. The detonation can be caused by any kind of insult to which the primary explosive is sensitive. Things like electricity, including static electricity, heat, friction, shock, that would be impact, something like a hammer, that's a mechanical impact, or even things like radio and cell phone transmissions. So just bear this in mind, because when you are in a place, if you're a police officer, you're in a place making an arrest, doing an investigation, you're a firefighter, you're there for a call, you're an EMT, you're there responding to some kind of emergency. We want you to be able to start to recognize locations and people that may be making bombs. Looking here at slide 22, you can see how these components get put together to make a bomb. And you can see it's pretty low tech. I mean, the battery is just a battery that you buy at the 5 and dime. The switch is a 79-cent switch from the hardware store. The initiator, the blasting cap, is something that could be commercially bought or stolen from a construction site. The only really hard part to get is the explosive. In this case, you've got a secondary explosive of TNT. But, you know, with a little ingenuity, little false credentials, or just stealing it, it's not all that hard to get. Shrapnel is easy to get. You put it all together, you got your basic criminal bomb. Very simple, very low tech, very easy to make. If you take a look at slide 23, what you got here is your basic car bomb. I can't remember if it's 150 or 300 pounds of ANFO that's in the back of that car, but it's only a couple few 50-pound bags, inexpensively bought anywhere. You see your secondary explosive on top of the ANFO that's going to ignite that tertiary explosive, that ANFO. And if you go to slide 24, you can see what's left of that car once that explosion happened. Now, remember that that was only a few hundred pounds of ANFO in the back of that trunk. Most car bombs, the entire car is packed. You know, every space is packed as full as they can make it, except for the suicide bomber or the driver. So what you're seeing in slide 24 is the result of a very small car bomb. What you would see if you were responding to the site of a deliberate car bombing would be even less residue of the car, and you can imagine a huge amount of damage to the surrounding structures and people. Let's take a look at what a briefcase bomb could do. If you look at slide 25, you can see the explosives sitting in the briefcase there. You can see it's a very small volume of explosive. I mean, it doesn't take up even half of the volume of that small briefcase. And you can see the building sitting next to it. It's actually a 2-room building. You should realize that this building was actually built to construction code. So it's not some flimsy thing that was just held together with a few tacks. It's actually a real building that would meet building code. And you can see what just that small amount of explosive in the confined space of a building will do. There's very little of the building left. The point here being that it only takes a small amount of explosive to do an awful lot of damage. Now, these photographs that you've just seen actually came from New Mexico Tech and from a couple of programs that they put on free for first responders. One was incident response to terrorist bombings, and the other was prevention and response to suicide bombing. You can go, as a first responder, you can go free to these week-long courses, and we encourage you to if you can. The more information on how to do that or where these resources are is contained at the end of this program. You know, we're all used to seeing the movies where the building explodes and the hero gets thrown through the air and gets up and walks away and just has a few bruises on him. Well, that's not real life. As we saw in the previous few photographs, just a small amount of explosive can cause an awful lot of damage. If you add shrapnel to the mix, you add a tremendous amount of lethality, of course, to that explosion. The explosive itself, that is, without any shrapnel, without any mechanical damage, just the pressure from the explosive can do a lot of damage. On slide 27, you can see what some of the PSI, what some of the pressures are that are generated at various distances from some typical kinds of explosives, like 6 pounds of C4, 300 pounds of ANFO, which is what was in the trunk of that car that we saw. And you can see that you get some very high PSI numbers at a reasonable distance away from the explosion. For instance, 300 pounds of ANFO, 100 feet away, talking 4 to 9 PSI. And these are conservative estimates. It can go higher or lower depending on the exact circumstances, reflections and things like that. Well, what does that mean? What does 4 to 9 PSI mean? If you're 100 feet away from a car bomb with a small amount of ANFO in it that goes up, well, 1 PSI will knock you over or knock you on your butt. 5 PSI will rupture your eardrums, cripple you for life by making you deaf. 30 PSI will damage your lungs, and 100 PSI will kill you just like that. Now, You have to realize that if these pressures are reflected, for instance, if this car bomb went off in a city and you had buildings that were reflecting the pressure, it's just going to amplify what the bomb itself is doing. The point here being that explosions are not anything you want to be anywhere near around. You want to get it out of your head that it's like the movies where you can just be thrown through the air because the building blows up or the car blows up and you walk away. When one of these bombs goes off, it does a lot of damage and it kills a lot of people. Now, of course, it's not just the shrapnel from the bomb that could kill you or hurt you. It's not just the overpressure that could kill you or hurt you. It's what happens when everything around you starts to crumble and fall in on you. An awful lot of deaths from bombs occur because of that. If you look at this chart, for instance, look at how little pressure it takes for glass to shatter and break. Falling glass, of course, is an extreme hazard, very deadly. And some pretty gruesome stories came out of the September 11th incident along those lines. If you look at, for instance, the reinforced concrete walls, you can see it doesn't take that much overpressure compared to what bombs produce for concrete walls to start to crumble and break. So the thing to take away from this is it doesn't take a very big bomb to cause structures to collapse and crumble. And by so doing, they just amplify the death, they amplify the danger, and they just make your job a lot more difficult.